All right, well, welcome back. So in this section, we're actually going to be introducing another algorithm for actually solving one of these discrete log problems. In this case, we're going to be looking at something that's commonly referred to as a collision or a meet in the middle approach. So just like the name suggests, what we're going to be doing is that we're going to be handed one of these discrete log problems, and we're essentially going to be chipping away at this thing from two different sides. At some point in time, we're going to collide, or we're going to meet in the middle, and we're going to use that information and actually springboard us to the overall solution. So this algorithm is actually pretty slick. It is actually pretty easy to implement in this case. So in a little bit, we'll go back and actually show the Sage code that actually runs through this overall computation. And it is our initial kind of big improvement upon the kind of classic brute force approach. It's not the fastest way to do a discrete log problem, but it is kind of our first step away from doing things brute force. We're going to be looking at a couple different algorithms for solving this thing, so we're going to be slowly refining this thing and starting to look at different improvements and things like that, but it does at least get us moving in the right direction. So to kind of baseline everything out, let's actually jump back to this brute force approach to kind of see what is it going to be worst case scenario. In this case, let's look at a classic little toy example. So in this case, we have the congruent 7 to the x, which I'm claiming is going to fire off a 19 modulo 23. A couple things to note right away is that number 23 is prime, so I'm at least in a pretty nice situation right from the get-go. The thing that makes this one really nice is that number 7 is in fact a generator. The idea is that if I take 7 and start raising it to various powers, it's actually going to cycle through all of those numbers 1 through 22. So at some point in time, I am going to fire off the value of 19. The way that I can actually see that 7 is going to be a generator is again achieved by looking at the order of this thing. In this case, the order of 7 is of a full order, in this case the number 22. The idea is that 22 is that prime, that is 23 minus 1. If you look at this number 22, you can actually see all of the possible orders that 7 could have had. The idea is that the order of this number has to divide 22. So if you look at 22, you see that it factors pretty easily as a 2 times an 11. So the only 4 possible orders that 7 could have had are the numbers 1, 2, 11, or 22. So if you take 7 and raise it to the first power, you see that it fires back a 7, so it's not a 1, so it's not order 1. If you square it, it's not going to fire off a 1. If you raise it to the 11th power, it's not going to fire off a 1. So you can see that we must have a full order of 22. So it's a nice thing is that equation is guaranteed to have a solution. If I change the 7 to something else that is possibly not a generator, we may not actually see an overall solution. The important thing in all of this is that you can see how long it's going to take for us to guarantee a solution emerges. The idea is that if I start taking this number 7 and begin raising this thing to various powers, well, I know that once I get to 22, I'm back to 1, and then this whole process is going to start again. So in this case, I know that I'm going to find that answer of 19 before the order. Once I'm at the order, I'm back to 1 in this case. And in general, if you give me some number that has, let's say, order n, I know that this process is actually going to terminate in n steps, if it actually has a solution. The idea is that if I change the 7 to something that was not a generator, I may or may not achieve the 19. I know that if I do see a 19, it's going to occur before the order. So that's given me this upper bound of a capital N. In this case, you can actually see that the number 19 is achieved at level 17. So as you start taking various powers of 7, it takes all the way until 7 to the 17th before it actually fires back the number of 19. So these numbers are actually going to be really important as I move toward this meet in the middle approach. This is actually going to be one side of this thing, is that I'm still going to be raising powers of 7, but I'm not going to have to go all the way to the 17th power. There's going to be a nicer stopping point in this case. So that's my first approach, is that I have this nice trivial bound that I'm going to go from one side, slowly increasing powers. And the thing that you want to do is you want to start thinking about ways to do this a little bit more efficiently. The idea is that when I start looking at 7 to the 4th, I don't want to do a full-fledged power mod operation on 7 to the 4th and then 7 to the 5th, because I have information that's actually achieved before that. The idea is that as I start to begin this list up, I'm going to start off with a 1, and then I go to a 7, and then if I want to get a 7 squared, technically I'm taking the last number multiplied by 7. Which in this case reduces down to a 3. So that's actually where this process starts up fairly nicely, is that if I look at taking 7 cubed, I don't have to full-fledged cube the 7. All I have to do is I have to take the last answer, which is 7 squared, and then multiply it by a 7, which in this case is going to fire off a 21. Same thing for the 7 to the 4th. What I'm going to do is I'm going to take the 7 cubed, i.e. the last answer, and then multiply that thing by a 7, which in this case is going to fire off a 9. So that's going to be one of our huge saviors for actually some computation time, is that I don't have to do this modular exponentiation algorithm every single time. That would be pretty obnoxious to have to do over and over and over again. The idea here is that I'm just building this thing up by taking the last number and then multiplying it by a 7. So if you want to see a slightly more formal write-up of why the upper bound for this thing is going to be achieved in n steps, I have just a really quick sketched out argument. But the idea here is that as you take larger and larger powers, once you get to the order, you're back to 1, and then you're going to start cycling in on yourself again. So you know that if you have some g that has order n, then this discrete log problem, attacked via a brute force approach, is going to be solved in O of n steps. So that becomes my baseline that I'm going to work with, is that every other algorithm that I'm going to try to implement had better do better than that particular bound. If I'm doing worse than trial and error or this brute force approach, I'm doing something wrong. So I really do want to make that n change to much nicer functions.